Let us see how to insert elements into a AVL tree using the rotations. So, I have to insert an element 21 for example first. So, it is very simple 21 node empty tree with only one node. Then the next element is 26 for example, right. So, we have to follow the rule of binary search tree, where we have to insert 26. See, 21 has two child, one is left, other is right. Okay. So, according to binary search tree logic, if the number which I am inserting is greater than the root, it has to come on the right hand side. So, 26 comes here. Okay. Then next element is 30, right. So, I am inserting an element. Where should I insert 30? What is the logic of binary search tree? Check if this element which I am inserting 30, is it greater than 21 or less than 21? It is greater than 21. Then go its right child. Again you have another root here 26. Is this 30 greater than 26 or less than 26? It is greater than 26. So, 30 will be inserted here, right. At every stage I have to verify whether it is no AVL tree satisfying the property of AVL tree or not. So, 26 was balanced, 21 is balanced. Now, since I inserted 30, check is 26 balanced? Yes, it is balanced because 0 and 1 difference is 1, satisfied. What about 21? The left subtree height is 0, right subtree height is 2. Okay. Therefore, the difference is 2. So, this node 21 is unbalanced. Let this be my x. This I have identified the x. Now, insertion of which element made this 21 as unbalanced? This element 30. So, where did I insert it? X corresponding left right child in its right subtree has come. Okay. So, it is right rotation, that is case 2, case 4, right rotation. What we have to do here, right? How do you do the rotations here? You identified that case. Now, you have to rotate it to the left hand side. You have to rotate to the left hand side. So, how do you rotate it left hand side? Simple. The rule algorithm of left rotation is simple. See, this is your x, make this as your w. Okay. X already we know, I have identified the x. X right, make it as w. Okay. X right, make it as w. This is my w. Then whatever elements are there on the left of w, whatever elements are there on the left of w. So, whatever elements are there on left of w should become x right. Okay. Should become x right. Okay. This is the why. Suppose there is one more element here. Let me take some 25. Right. When I am doing left rotation here, I am trying to balance this. When I am doing left rotation here. Okay. So, when I am doing left rotation, this 21 has to come down, 26 has to go up. For that, if I take 26 up, it is becoming something like this. 26 is coming up, it is linked with 21, also 30 and also 25. This is not a binary search tree. So, what we have to do, that is why whatever elements are there on the left child of this w, okay, whatever elements are there on the left child of w, those you add it as right child to 21. Those you add it as right child to 21. Okay. So, this got broken and it joined here towards right side of 21, right. Now, it has become, now what I can say, now w has some left, w of left will be x, w's left will be x. This left we have deleted, attached to 21, no. So, this is got deleted now, this is empty this side. I am deleting this node and linking here x 21, x like this. Now, this is also deleted. It has a right, what is that? 25, right. Like this you have to rotate. Now, see, it is balanced and also it is satisfying the property of binary search tree. Why? The new tree is 26, it has become my root. Elements on the left subtree are less than 26, right subtree are greater than 26, and every node is balanced here, right. So, I will just draw the root, the base diagram for inserting the next element. So, you have 26 here, you got anyhow we didn't have any element like 25, no. So the tree will become simply like this 21 and 30, since W didn't have any elements, right. Let's insert the next element. Okay, so next element to be inserted is 9. So where do we have to insert 9? According to the logic of binary search tree, left side of root, again in that root 21, left side of 21, I have to include 9 here. This is balanced, there is no problem in this. You can check the height of each node, everything is balanced. The utmost difference of the heights is 1, so it is a balanced tree. Okay, next, the next element to be inserted is 4. So where I have to insert 4? As per logic of BST, I have to insert to the left of 9, 4 here. Because of this, some node became unbalanced. That we have to check everything, whether it is balanced or not. Every iteration we have to check the logic. Okay, so what is there here? So 9 is balanced, 21 is unbalanced. Okay, 21 is unbalanced. So let me write the rough diagram here. 26 has 21, 30, this is having 9, this is having 4. This became my x. Okay, so x is unbalanced. What I have to do? I have to rotate it towards right side. I have to rotate it towards right side. Why rotation right? Why? The x left child left subtree has been inserted, you have to do right rotation. Okay, you have to do right rotation. Why? The element has been inserted on the left child, its corresponding left subtree. So you have to do right rotation. How to do right rotation logic? How to apply the logic of right rotation? So x is already, you know, x we already know. X left will become W. So this became my W. Okay. Then whatever elements are there to the right of W, whatever elements are there to the right of W should become left of 21. This is my x, no. So whatever element is there to the right of W should be attached to x left. It should be attached to x left. That element should come to the left hand side of x. Since we have no elements here, this step has no meaning. Then next, now you break this connection. We have to break this connection. How do we break this connection? Simply make W left, okay, W right equal to x. So with this what will happen? This 21 will come down, this 21 will be broken down and it will come here as a new element 21 like this. Okay, right? And then this is anyhow there, this link is there. Okay, so this way we are trying to delete the x, we are trying to bring it as a new node here. We are trying to bring this x as a new node here and we are linking these elements. Now the tree is balanced. Okay, so the updated tree becomes something like this. So you will have 9 here, this side it is 4 and this side it is 21. Okay, so that way we are writing, the algorithm is very simple. Let us see one case for double rotation and then you will understand it much better. Double rotation. So let me insert 14, the next element 14. Okay. Now where should I insert 14 as per the algorithm, binary search tree algorithm? I have to insert 14. See, 14 is less than 26, 14 is greater than 9, then it came 21, 14 is less than 21. So I have to insert here 14 like this. Okay. Now verify any node became unbalanced. So 21 is balanced but 9 is balanced, 26 became unbalanced. The root 26 became unbalanced. Why it became unbalanced? Because its left subtree height is 3, right subtree is 1. So the difference is 2. So this 26 became my x. Okay. Now what I have to do? Okay. So let me draw that here. 26, it is having 9, 30, this side it is 4, 21, this side I am having 14, right. So this is my x, x corresponding left side, it became, because of left insertion it became unbalanced. So x corresponding left child a left insertion, again insert in the right subtree, insertion in the right subtree. So you have to do here left right rotation, we have to do left right rotation, meaning a single left and then a right, we have to do a single left and then a right. Okay, so what is my W here in this case, right? So this becomes our W, this becomes our W, right? So what we have to do here in this case, let's just see the algorithm here for that left right rotation, right? See, Z left, that is the node which I am taking, I am doing single rotate right with Z left. Okay, so here this is my W, I have to do single right rotate, right? We have to do left, sorry, LR, so we have to do left and then right. How to do this? What is the logic of single? We have already seen 2 times, just try to understand this. Single rotation, only left rotation, okay, single left rotation, meaning I have to shift it towards this side. How do I shift it towards this side? What you can do? See, whatever child, okay, whatever children, this is my 21, this is my W, X has become unbalanced, so Z left I am making this as W, right? From this W I have to do a left rotation, I have to do a left rotation. So how we do a left rotation here? See, this is W, okay, let's take the simple example, 26, not a complex one, just see this, 9 and then 21 and then 14, okay, this is my W, this is my X. We have just seen the algorithm how to do left rotation. What we have to do in left rotation? Whatever children are there for this W, that should become child to X, no? That should become child to X, right? Single left rotation. Whatever child W is having, that should become the child, left child to 26, that is X. Okay, so this will broke here, this 21 also will go, this 21 will become a child to X, that is 26. This channel has become now 30. Okay, after this, right, after this, what about this 14? 14 also will be linked to this 9, it has to be linked to 9, like this. Okay, whatever in iteration, because it is recursion, no, in iteration again make this as your W and do the process, make this as your X and do the left rotation. Okay, so this way after one single left rotation it changes to this format. Then you have to do a right rotation, you have to do a right rotation. Okay, how do you do right rotation? You have to bring this down and take this up. Okay, so 21 will become root, on the left 26 and again on the right 30, this side 9 which is having 4 and 14. What is the logic of a single right rotation? When you are doing single right rotation, right, if this is your W, this is your X, okay, so this, what we say, whatever child are there to W, whatever children are there to W, those will become the left child of X, but it does not have anything, so there is no left child to X. That's it. Then break this and make this as your root, 21 became root. Okay, this way it has become balanced. So the updated tree, one last operation we will see. I'll just note down the updated tree with us. So updated tree here is 21, it is having a right child 26 and another right child 30. This side it is 9 which is having 4 and 14. Okay, one last element in insertion we will see. Right, let's insert the next element 28. Okay, where should we insert 28? Right, so for inserting 28, I should be inserting it here. As per BST logic, 28 is greater than 21, it is also greater than 26, 30 it is less than 30. So here comes the 28. Okay, now find out which node has become unbalanced. Which node has become unbalanced? See, 30 is balanced, 26 has become unbalanced. This has become unbalanced. Okay, so now I have to do, now which case is this? Which rotation do I have to apply? First identify the case. See, X its right subtree a left child has come. Its right subtree a left child has come. That's why right subtree a left rotation I have to do. From the mistake, from the violation itself, you can identify which rotation to do. For x, where was the new element inserted, because of which the x became unbalanced. If you see, 26 is having a right child 30, a new element is inserted left of 30. So, for x, its right child and its corresponding left subtree. So, right left rotation we have to do. Okay, we have to do right left rotation in this case. So, how do you perform? So, it is single do single right rotation, then you do single left rotation, single right and then do single left rotation. So, what we have to do here, first thing you have to rotate only this thing. How will you rotate this? If this is the case, if this is your x, this becomes your w. Okay, what you have to do here, rotation, when doing rotation, what we are trying to do? See, when you are doing right, first do right rotation, first do the right rotation. So, x to do right rotation, this w should know whatever left child, okay, whatever left child this right child this w is having, okay, will become the child of this 26, will become the left child of this right child of this 26. But do we have such kind of element here? No, right. So, we will rotate this, this will become again this structure will change to something like this. Okay, these three you observe. For this 30 will come here, then comes 26 and then comes 28. Okay, then you do one more left rotation, one more left rotation. So, with this 28 and here 30, right. So, this tree will change to, no, the after 21 we will have a link like this, first right rotation and then left. So, which one you are rotating? X, you are doing right rotation and then you are doing left rotation. Okay. So, with this, no, we understood all these 4 different types of rotations. Identifying the case, that itself will tell us that the tree is balanced or unbalanced. So, this will become something 28 here, 26 this side and 30 this side. See, perfectly balanced. Okay. So, this is about rotations in AVL tree. While inserting itself, we are checking at every level whether the tree is satisfying the property of AVL tree or not, right. We will see the implementation part.